Hello everyone, today I'm going to talk about circular motion, and we'll start out talking about uniform circular motion in section 5.2 of your textbook, which is referring to an object that travels around a circular trajectory, right? It's the same distance from a common center at all points, and uniform in uniform circular motion just means that the velocity is not changing, the speed is not changing as the object travels around the path there. So the velocity is changing because velocity is a vector quantity. Right? So I've drawn up here, there's an object, the object is traveling at velocity v1 at this point. At every point it's traveling at a velocity that's tangential to the path, the circular path. So at some later time, it's going to have a velocity v2, also pointing tangential to the path. The velocity is going to be different because that vector is pointing in a different direction. However, the length of the vector is going to be exactly the same. So that means as the object travels around, right, at one point it has a velocity vector v1, at a later point it has velocity vector v2, but the magnitude of those vectors is always going to be the same, meaning the object is in uniform circular motion, or it has some common constant speed v. Now we use the time that it takes to travel around one full circle and come back to the point where the object started. We call that the period. So the period is denoted by this capital T here. And instead of talking about the period, which would be how long does it take for this object to go around, if you wanted to talk about a different circular motion quantity, say, instead of saying how long does it take this object to go around, you want to ask a slightly different question: how many times will this object go around in a given time period? Then you'd be talking about the frequency, right? So an object that has a period of 1 second travels around a full circuit every second, and that means its frequency would be once per second. So frequency is 1 over t. If an object travels around its circular path in 2 seconds, then the period would be 2 seconds. The frequency is once every 2 seconds, or 1/2, 1 over seconds would be the units. And there's another way of talking about the units of frequencies. We usually write these in terms of hertz, and a hertz, 1 hertz, is just 1 over second. So the frequency is just 1 over the period. It's referring to the number of times something happens in a given window of time. It has units of hertz, or 1 over seconds in SI units. So let's talk a bit about about what changes in a period, within one period t. The object will travel a distance of 1 full circumference of this circle. So the distance that it travels will be equal to 2 pi times r, and the angular change in its angular orientation, here I've denoted the angle between these two velocity vectors to be theta here. In 1 full period t, the angle changes by 2 pi radians. And we're going to mainly use radians. That'll be the most helpful quantity for you to use in talking about circular motion. So here, a distance of 2 pi r is traveled, and an angular change of 2 pi happens within a time t, the period. So that means that I can take these two quantities and I can say something about the velocity from each one of them. If an object travels 2 pi r in a time span t, that means its speed v is 2 pi r over t. And if the angular change is 2 pi, we can define another related kind of velocity called an angular velocity. We denote that omega, where omega is the change in the angle over the change in time. And that is obviously going to be a constant as well. If v is constant, then omega will be constant. And in a time t, the angular change is 2 pi. That means that omega would be 2 pi over t. So this is in the case of uniform circular motion, where an object travels around a circular path and its speed is always the same. So as I said, the speed of the object as it goes around is constant, but the velocity vector is not constant because the velocity vector points tangential to the path as the object traverses its trajectory. Now what that means is that there must be some acceleration the object is undergoing. Acceleration is the time derivative of velocity by definition, and the velocity vector is changing in time, meaning that there must be some acceleration. Now, if I take an example here of an object that's traveling in a circular path, it's not quite uniform circular motion, but use your imagination, it's pretty close. I can try and keep the velocity, I can try and keep the speed constant as close as possible. So you'll see that the acceleration here must be pointing in towards the center. That must be the direction that the acceleration vector is pointing. Now, why is that obvious? Well, because it should make a lot of sense that the force involved on this object is going to be pointing in towards the center, because the force that's keeping this thing moving in a circle is the tension in the string. All right, since the tension in the string is always pointing along the string, and the string is always tied between my hand, the center of motion, and the object itself, that means that the force is always pointing in towards the center. And since the force is always pointing in towards the center, the acceleration must be pointing in towards the center as well. So, anytime that you have a force that's pointing in a direction other than the velocity vector, you'll always have some kind of curved motion. So when we talked about projectile motion, there was a velocity that was traveling, say, along some angle to the ground, and the force of gravity is always pulling down, so you get a parabolic path. Right? In this case, what you have is a force that's pointing in towards the center of the motion. In that case, it was the tension in the string. And the velocity, of course, is pointing tangentially to the string. Now, if I were to take that path, if I were to take that duct tape roll as I was flinging it around and cut the string at any given moment, or what I could just do, this will be approximate here, but I can take this thing and just let go. What you'll see is that as I let go, I'll try and slow that down, but you can see that as I let go, the object just flies off in whatever direction it was traveling at the time. So if I cut the string, say right here, at this moment where the object's velocity vector is v2, it's going to travel not outwards towards the outside there, it's not going to travel inwards, it's not going to continue curving as it goes along, right? It's going to go in a straight line. I've now removed the centripetal force, or the force that's pointing in towards the center of motion. So that means it will travel right tangentially to the path. And that means, so the acceleration is brought about by some force that's pointing in towards the center. The acceleration, then, is pointing in towards the center. So we use this word centripetal, which is Latin, and it means center pointing. Centripetal. The force that brings about circular motion is a centripetal force. The acceleration bringing about centripetal motion is a centripetal force. Is a centripetal acceleration. So I've just discussed the direction of the acceleration vector, how it's pointing in towards the center, as is the force that brings about the circular motion. What about the magnitude? Well, the magnitude of the centripetal, this is A sub cent, C-E-N-T, short for centripetal. the magnitude of this acceleration vector is equal to the speed squared divided by the radius, v squared over r. Now, I'm not going to derive that for you, but you can look in section 5.2 in your textbook. It's right there within the first page and a half. The velocity, the magnitude then of the acceleration would be v squared divided by r. So I'm not going to derive this, like I said, but I will talk about just why this might make sense to you, right? If I take the object moving around its circular path and I pull, say, the string tighter, then the centripetal force increases and the velocity would increase as well. So that would make sense. If the force increases, the acceleration will increase and the velocity will increase as well. Say if I start spinning that thing faster, I would go and do it, but I can't find it. I don't know where it is. The velocity would increase, so this makes sense. Also, the radius, if I were to take the thing and make it very, very large, then you would see the object, rather than moving around like this, it would start going more slowly, right, if it was moving out towards the edge. So for example, you see this with the planets. The planets are on approximately circular paths. A circular path is a very close approximation. And so if you look at the orbit of, say, Neptune or Jupiter, which is a lot farther from the sun, they have larger r. Their value of r is larger. The radius of their circular path is much larger. They're farther away from the sun. And of course, the force that the sun exerts on them is much lower because they're farther away. And the centripetal acceleration on all of the planets turns out to be fairly approximately constant for reasons that we'll talk about in the next chapter. So what you see is then the radius getting larger, you have a lower centripetal acceleration. So the magnitude of the centripetal acceleration then is v squared over r. I like to use the little vector, the unit vector r hat, to denote to be the unit vector that's pointing out from the center of something along the radial direction. So if I wanted to write the total radial acceleration vector, then I would write that it's equal to v squared over r, that's the magnitude, times minus r hat, right? This denotes that it's pointing in towards the center. Now, very quickly, I just want to talk about what happens if we relax this assumption of uniform circular motion and talk about just general circular motion. So the interesting thing about general circular motion, say that you had an object traveling around a circular trajectory and it's not necessarily going at the same constant speed. The interesting thing is that the acceleration in the radial direction is always going to be v squared over r, no matter what. It doesn't matter if v1 up here is different than v2 over here. Up here, the functional form of the acceleration will be exactly the same. Up here, the acceleration will be, the radial component of the acceleration will be v1 squared over r. Over here, the radial acceleration will be v2 squared over r. At every point, the centripetal component of this acceleration would be whatever the velocity is at that point squared divided by r, pointing in towards the center. There would also be another component to the acceleration, so the total acceleration vector then would be a radial plus a tangential. Just write a tan for a tangential. And the tangential component of the acceleration would come from the change in the speed of the object in the case of general motion. So what we would have here is the exact same radial form as is written up here, and the tangential component has a magnitude that would be equal to dv dt. Now note that that v there, that is the magnitude of the velocity vector, so it's the speed. This is then d magnitude of v dt. And that makes sense because if you think about an object traveling around a circular path, its acceleration in the tangential direction is going to be just the change in the speed at that given point, right? And it'll point tangential to the path. So if I were to draw an acceleration up here for, say, an object down here, it would be traveling this way. The velocity vector would be tangential to the curve. And its acceleration vector would then be, grab a different color, the acceleration vector would have two components to it. It would have a radial component, a radial, v squared over r would be the magnitude of that component, and it would have a tangential component if the velocity, if the speed was changing in time, and that would be out in this direction. This would be a tangential. Right? It makes sense that the tangential component of the acceleration would just be the rate, the time rate of change of this tangential speed. And our overall acceleration vector, the resultant, would be the radial component in the radial direction plus the tangential component in the tangential direction. That is section 5-5 in your textbook, so you can learn more about that there. My primary concern in bringing this up is that in a moment I'm going to start talking about centripetal dynamics and centripetal forces, and I want you to be aware that when I'm finding a radial force, the force that brings about centripetal motion, that I can always find the radial force that's brought about by other forces, and I can set that equal to m times a radial, and that object, even if it's not undergoing uniform circular motion, if it's just undergoing circular motion, so long as I've found the radial, all of the radial components, contributors to the radial force, I can set that equal to m times a radial. So I can do F radial, the net radial force, and I can set it equal to m times a radial. And that is always going to follow this same functional form here. This is going to be a minus mv squared over r times a r hat vector, right? There's a minus there because it's in the negative r hat direction. R hat points out from the center. Negative r hat points then in towards the center. Let's move from talking about circular kinematics to circular dynamics. So circular dynamics concerns the forces that bring about these centripetal accelerations and keep things moving on circular paths. As is always the case, Newton's second law tells us that F equals ma, and that's a vector relationship. So we know that that is true for each of the individual components of the force and the acceleration. The relevant components here are not x and y, but the best way to express this would be in terms of the radial and the tangential components of the force and acceleration. So I can take the radial force, the radial component of the force, and it will be equal to the mass times the radial acceleration. And the radial acceleration, as we just discussed in circular motion, is v squared over r. So very quickly, if you did want to express this in terms of angular speed instead of tangential speed, it's easy enough to convert between the two. Tangential velocity, or tangential speed, is just equal to the radius times omega, the angular speed. So to convert between the two, you just multiply by r. So we'll work mainly in terms of the tangential speed in this chapter. By the time we get to chapter 10, we'll be talking more about angular quantities. So if we sum up all the forces in some free body diagram problems, we can find properties like the speed at which the circular motion, the object in circular motion is traveling. And if it's in the case of uniform circular motion, you can find properties like the period and the frequency. And this is kind of the direction that we're heading once we start talking about these problems in terms of free body diagrams. Okay, so this force, the forces that bring about this circular motion, are called centripetal forces, meaning center-pointing forces. There's one common misconception that I should address, which is the idea of centrifugal forces. Now, centripetal, like I said, is center-pointing. Centrifugal is center-fleeing. It means something that points outward rather than inwards. And it's important to keep in mind that when you are in a rotating reference frame, things are a lot more complicated. So what we'd like to do is work in inertial reference frames. Remember, inertial reference frames tell you that those reference frames where Newton's first law applies, that an object in motion will remain in motion and an object at rest will remain at rest unless acted upon by an outside force. If you're in a rotating reference frame, then you're in a non-inertial reference frame. Newton's first law does not apply. What we like to do is draw up free body diagrams that tell us about the forces in an inertial reference frame. And because of that, we don't have to talk about centrifugal forces. In fact, because we're in inertial reference frames when we're solving our problems in Physics 1, centrifugal forces do not exist. They are fake forces, as is sometimes said. So let's talk about this problem here. So if you have a merry-go-round, so I'm just thinking of if I push my son on a merry-go-round. The merry-go-round goes round and round. Here I have it kind of at an angled view to you. He's sitting here on a bench on the merry-go-round. I push the thing around, it spins this way. And my son, the faster that I push him, he's sitting in the chair, he's going to feel pushed back against the chair. Now, you might give me this argument. You might say something like, the centrifugal force here can't be faked because he's sitting there on that park bench. He feels pressed against the back of the chair. So there must be this force pushing out on him. And the reason why I can still say that technically speaking the centrifugal force is a fake force is not because he's not feeling anything, it's because he's in a non-inertial reference frame. Because he's in a rotating reference frame, he's going to feel this force pushing out on him. When I solve the equations of Newton's laws and try and figure out the properties of his motion as he goes around, I'm going to be doing so from an outside reference frame. I'm the person standing outside of the merry-go-round watching him go around. And from my point of view, I do see a force, but it is just the normal force exerted by the chair on his body, pushing him in towards the center of motion. So, in this case, I've drawn here the normal force pushing him in towards this central axis here that I've extended up from the center of motion of this merry-go-round going around. So if I wanted to look at this from the side view, then if I look at it perfectly from the side where the disk is straight on here, he would be sitting here on this chair, and he's sitting right, his back is right up there against the chair. As the thing is moving around here in the plane of the board, the force that the chair exerts on him is going to be pointing in towards the center here. The normal force is what brings about the centripetal motion as he travels along. So what I need to do then is just sum up all of the forces in the radial direction. In this case, it's pretty easy. There's only one. There's just this normal force here. And I can set that equal to m times the radial acceleration, or mv squared over r. So just the idea of a centrifugal force is something that you're only going to deal with if you're starting to go on to do it, solving mechanics problems in non-inertial reference frames, and you're not going to do that in an intro physics course. So you can get rid of the idea of centrifugal forces for now. So that it's the centripetal force, or the one pointing in towards the center, that you're concerned with. Now, a key thing that I also want to emphasize is that when you draw up a free body diagram for some centripetal force type of problem, you are never going to draw a vector that is a centripetal force on your free body diagram. And the reason is that centripetal forces are something made up of other real forces. There will be, so in this case here, we have a normal force pointing in towards the center. That happens to be our centripetal force. But I wouldn't draw F centripetal here on the free body diagram, because the centripetal force is just an idea. It is an idea that comes out from what we know about circular motion, and it is made up of those real felt forces in there. Those real felt forces involved in the problem, those things bring about, this centripetal force, which is more of a mathematical concept. So let me just explain. So if my 2-year-old daughter comes and she runs up, as she sometimes does because she likes to follow her brother around, if she runs up and she leaps and jumps onto my son's lap, right, she'll exert a force on him. I'll always go in keeping with keeping all forces in red. She will exert a force on him, right, pushing out on him when she jumps up onto his lap, right? So this would be F, I'll call this Fs, or force that Sally exerts on Daniel. My daughter's name is Sally. So at this moment, when she's just leaping onto his lap, right, there would be a normal force pointing in. There would be this force, Sally exerts a force pointing out. Now, what is the centripetal force then in total at that moment? Well, if the force that Sally exerts is entirely in the radial, outward in the radial direction, and the normal force is entirely inward in the radial direction, then that means that the centripetal force would be equal to Fn pointing in minus Fs, the force that Sally exerts pointing out, right? The minus sign comes because Fs is pointing in the opposite direction. So that would be the centripetal force, or in other words, the radial force up here. I'll write centripetal and radial. They're going to be, for the most part, synonymous. But the centripetal force then goes down if there is a force exerted out on my son at that point. So still, I have a normal force pushing in and the force that Sally exerts pushing out, drawn on my free body diagram. I have no arrow that shows the centripetal force itself, because the centripetal force is composed of the other forces involved, that the radial component of the other forces involved. So now we'll do a couple example problems, and you'll see why this makes a difference. Hey, I got a little smaller. Okay, let's do a warm-up kind of example problem. this one right over there. So if you spin duct tape attached to a string around in a vertical orientation, then the centripetal force will change along the path. Draw all of the forces in a free body diagram on the duct tape as it goes around its circular path, especially at those 4 different points there, and then circle the radial forces. Why don't you pause the video and go ahead and draw those 4 different free body diagrams right now. All right, I'll assume that you've done that. So we have our circle here, and we had our 4 different points. What are the 4 different forces? The forces, the 2 relevant forces, as I'm spinning this thing around, are of course going to be gravity pulling down on the massive duct tape. We can pretend that the mass is, or that the string is massless because it does have a negligible amount of mass compared to the duct tape. And the tension in the string as the thing is being flung around in a circle. So the weight, of course, is going to pull it down in the exact same direction at every point. So there's mg down, mg down, mg. If you put fg or w for weight, that would be fine too. This is going to be pointing down in every case. This does not change with respect to the xy coordinates. But the tension, of course, will change with respect to the xy coordinates, if I were to draw right, xy. However, the tension will not change when it comes to the radial and tangential components. The radial component of the tension will always be however, the tension force will always be acting inwards in the radial direction. Right? So tension force is pulling in there. The tension force is pulling down in this case here. The tension force is pulling in that case. And the tension force is pushing up then at the bottom of the trajectory. So the final part asks you to circle all of the radial forces at these 4 different points. Well, tension is always acting radially. So you can circle tension in every case. What about the weight? Well, the weight is completely tangential on the sides here. Right? So I'm not going to circle that. I'm not going to circle that. The weight does act in the radial direction at the top and bottom of the circle. Here, it contributes to the centripetal acceleration, or the centripetal force. There, it pulls away, making the centripetal force less down here at the bottom. Okay, that one was kind of a warm-up. Now, on to what is example 5.13 in your textbook. A small ball of mass m suspended by a cord of length L revolves in a circle of radius r equals L times sine theta, where theta is the angle that the string makes with the vertical. Now, notice here, theta is fixed, right? It doesn't change with time. In what direction is the acceleration of the ball, and what causes the acceleration? Is part A. Part B, calculate the speed and period, or the time required for 1 revolution, of the ball in terms of L, the length of the string, theta, its angle with the vertical, g, the free fall acceleration, and m, the mass of the ball at the end of the string. Now, notice here that you're going to have to actually use a free body diagram and solve Newton's laws in order to come up with these equations. Why don't you go through those preliminary steps that I had shown you from before, read the problem, read it again, draw a free body diagram, set up a coordinate system, go through all of those steps and try and solve it yourself, and then you can hit play and I will solve it up here. All right, that might have been tough. It was the first one, but let's get started. Now, I've drawn my picture up here, and you can see the full free body diagram from the textbook right over there. I have my mass m and the string L, And this distance, right, from the object to its center of motion, which is the relevant radius that we've been using in the v squared over r for the centripetal acceleration, is this distance here, r, which is just L times sine theta. That comes from trigonometry. And I can then indicate my two forces here. There is the tension force pushing up in this direction, and there is the gravitational force, mg, pulling down in this direction. Okay, now if I wanted to use xy coordinates, I could set up xy coordinates like this. Right, I could call that x and this y. Right, and then you would see that the x acceleration is non-zero because this thing is moving around, but the y acceleration must be 0. Okay, now that's just because the object isn't changing in height, right? It's moving in a circle around this conical pendulum. So since the acceleration in y is equal to 0, this tells us something important about the sum of the forces in the y direction, right? The sum, the net forces in the y direction must be equal to 0. Now, what are the net forces in the y direction here? mg is pulling straight down in the y direction, and the tension T has a component that's also in the y direction, right? Tension is along this direction here, so I can take this angle here to get the different components of the tension, right? Tension times sine theta will give me the component of the tension in this direction here. Tension times cosine theta will give me the component of the tension pointing up in the y direction, right? So I will have then my net force in the y direction is going to be tension times cosine theta up minus mg, which goes down. This is helpful. This is useful because I can solve this, right, to get the tension. Tension is then adding mg to both sides of this equation and dividing by cosine theta, mg divided by cosine theta. So that's helpful. And now I can solve the F-net equations in the radial component to get the radial acceleration, and from that I can get the period of the pendulum and things like that. So note here that there's going to be two T's, right? One stands in for tension. The other one that's coming later is going to be for the period. Okay, what is the acceleration in the radial component now? What are the forces in the radial component? So note, I'm not going to use x per se, although at this snapshot here, x, the positive x direction, is precisely the radial direction. And it's not going to, the magnitude of the radial force is not going to change as the thing goes around, because this is uniform circular motion. So the x forces from this particular snapshot will give me the radial forces at every point. So, as I had said, tension pulling up this way, tension sine theta in this direction, in towards x. So, F net in the radial direction is going to be equal to just this one single force in that within the plane of motion, T times sine theta. All right. Now I already got the tension from my forces in the y direction, so I can just substitute that in. It's an mg over cosine. So when I plug in this mg over cosine into the tension there, I will have a sine over a cosine, so that just gives me a tangent theta. mg times tangent theta. Okay, and this is the net force in the radial direction. So it's equal to m times a radial times a radial. And I know from our earlier discussion that the acceleration in the radial direction is just v squared over r. Now notice that I put in little r here. It's not L. L is the distance, the length of the string, but the r here that we're talking about when we use radial acceleration is going to be the distance between the object and its center of motion, right? Its center of motion is not up here, right? Its center of motion is down here. So this is a key thing. It's very important. So I now have mg tangent theta is equal to mv squared over r. And also I know that v is 2 pi r over the period now, t. I'll put a little t sub p for the period there. We know this because the object is in uniform circular motion. So I can plug that in to this equation here to solve for the period. Now, doing this, it's sometimes helpful to put the radial acceleration in this form where I use the v squared over r equation. That's going to be this squared divided by r. And I can expand that out. This will give me a 4 pi squared, a single power of r now in the numerator, because I'm getting rid of this one in the denominator, divided by tp squared. Okay, so this is my v squared over r. I can plug that in on the right-hand side here, and this would give me, first note, right? M cancels out on either side of this. So I have a 4 pi squared r over tp squared is equal to g tangent theta. And the final thing that I have to do is to just solve this for t sub p, the period. So once again, we're limited for board space here in the physics basement, so I erased some things. I'm going to just solve this here for TP. So I took the equation and I brought it all the way back up here. And the only thing that I changed is I substituted in for r, L sine theta, right? That was the distance from the ball to its center of motion. And I put in for tangent on the right-hand side a sine theta over cosine theta. Now it's just a matter of doing some algebra. So I can cancel out the sine theta on either side here. And I can solve, I can take the square root of both sides of this equation. On the left-hand side, the square root of 4 pi squared over tp squared is going to be 2 pi root L over tp. And on the right-hand side, I'm just going to have root g over cosine theta. Now, multiply by tp on both sides, divide by root g over cosine theta on both sides, will give me tp equals 2 pi root tp is going on that side, L cosine theta divided by g. Okay, and that is my final answer. Okay, let's just think about whether this or not this makes sense. Does it make sense that at a, say, fixed amount of, when the forces don't change, would a longer string on the pendulum give you a larger period? Yeah, that makes sense. So it makes sense that the period depends on the period goes up as the length goes up. Cosine theta would be the cosine theta would tell you the angle with respect to the vertical, and that pretty much makes sense as well. So let's just, before we go on to the next problem, point out some of the key things that are going to show up in a lot of these centripetal force diagram problems. So first thing here, we had to use our knowledge that the acceleration in y was 0 in order to get this tension here to solve for something. So we couldn't jump right into the radial components and completely ignore the non-radial components, right? We needed that information that we had to get some of these quantities that we'll need in order to find our final answer. And the second thing is that we had to take all of the forces in the radial direction, sum them up, in this case there was just one, and set them equal to mv squared over r. Final thing, since this was uniform circular motion, we could substitute in for the velocity, or for the speed v, 2 pi r over the period t, and we also wrote down a nice intermediate quantity that you might find useful on your equation sheet later that expressed v squared over r, the centripetal acceleration, in terms of the radius r and the period here in this relationship right here. So this is a helpful thing that you might want to have written on your equation sheet so that you don't have to re-express this every single time. But do remember that this quantity would only be true in the case of uniform circular motion, and that the radial acceleration is v squared over r is true in every case of circular motion. It doesn't have to be uniform. All right, one more problem, and then I will cut this video off and I'll go and make another video that's shorter with just a couple more example problems, but this one I don't want to run too long. So 55 from your textbook. Tarzan plans to cross a gorge by swinging in an arc from a hanging vine. If his arms are capable of exerting a force of 1,350 newtons on the rope, what is the maximum speed he can tolerate at the lowest point of his swing? And it gives you the mass is 78 kilograms and the vine is 5.2 meters long. Okay, pause the video, go ahead and solve this one yourself. Okay, I'm going to assume that you've done that. Now let's go through and talk about the problem. So when it says that the maximum force that Tarzan's arms can withstand is 1,350 newtons, that means that essentially the maximum tension that the string can have is going to be 1,350 newtons before, in this case, it's not the vine breaking, right? It's his hands letting go. He's not going to be able to withstand any more than that. And of course, as he swings across, he's not going to be in uniform circular motion. But that's okay. It doesn't matter because as long as we can sum up the radial components of all of these forces, we can still set the net radial force equal to his mass times v squared over r, where v squared is the velocity, the speed at wherever he is at the specific point there. So we have a mass, we have the radius of curvature, which is 5.2 meters, and we know, of course, that his maximum velocity is going to occur when he's at the bottom of his swing, right? That they tell you that in the problem, but that just makes sense that he's going to speed up as he's going down, he's going to slow down as he's coming back up. So the only point that we need to analyze then is the one right at the bottom of his swing there. So I will draw my free body diagram. There is a tension force pulling up on Tarzan, and there is a gravitational force pulling down on him, right? His weight is mg. So if I set this to be the positive y-axis, then I can set our acceleration, our mass times acceleration in y to be the net radial force, right? We are only considering this point when he's at his lowest point in the swing, because that's the only thing that's needed for the problem. So this is F net in the radial direction, since at the bottom of the swing, the y direction is the radial direction. Okay, now MAY then is F net in the radial direction. It will be equal to, now not 0, right? If he was just hanging there, the acceleration in y would be 0. But he's swinging, there is a centripetal acceleration that is in the y direction. So this is going to be equal to m times v squared over r. All right, now at the tension, well, before we talk about that, let's say, okay, so the F net in the radial direction is going to be the tension force going up and the weight going down. Those are the two things that contribute. So this will be equal to the tension force going up minus mg, since the weight is pulling down. So here we have tension minus the weight is equal to mv squared over r. R is the length of the vine. All right, now we want to consider a special case, right? The special case is at T equals T max, the maximum tension force that Tarzan's arms can withstand. That's where we have V equals V max. So let's analyze that particular scenario. Max squared T max here. So we know T max, and we were asked to find V max. We know M, we know R, the length of the vine. So we have one equation with one unknown. All we have to do is solve this for V max and plug in some numbers. So let's do that. We'll take this problem here, and we'll multiply by R on both sides and divide by M. So we'll have R over M times T max minus R over M times mg. Right, so the m's will cancel out there in that term, equals V max squared, which means that V max, and if I just take the square root of both sides of this equation here, is going to be equal to root R over M T max minus RG. Okay, and then all I have to do is plug in some numbers. And if I plug in, R is 5.2 meters, T max is 1350 newtons, G is 9.8 meters per second squared, I get that this is equal to 6.2 meters per second. Okay, that's a good example of a problem where we have circular motion, but not uniform circular motion. I'm going to stop the video now. There's a couple more example problems in the next video, which will be coming later today, in case you are not quite ready to do your homework from just these few example problems.